So here's something worth thinking about as you settle in tonight. Right now, as you're lying there, the earth is pulling you down into your mattress with a force that's been governing everything on this planet for billions of years. Gravity. It's so constant, so reliable, so utterly inescapable that most of the time we don't even notice it. But for almost all of human history, there was this dream, this stubborn, ridiculous, beautiful dream of somehow pushing back against that force hard enough and fast enough to just leave, to climb up off the surface of the world and keep going. And the story of how we figured that out, how we actually built machines that could do that, is one of the greatest engineering stories ever told. So let's talk about rockets. Let's talk about how they actually work from the very beginning, and let's take our time with it. There's no rush. We've got all night. Now, the first thing you need to know, the absolute bedrock idea underneath everything else, is something so simple it almost sounds too obvious. A rocket works by throwing stuff out the back really fast. That's it. That's the core of it. If you were standing on a frozen lake, perfectly still, and you threw a bowling ball as hard as you could in one direction, you'd slide backward in the other direction. You'd move, not because anything is pushing you from behind, not because you're pushing against the air, but because of a fundamental law of physics. Every action has an equal and opposite reaction. Newton's third law. You push the ball forward, the ball pushes you backward. A rocket does exactly the same thing, except instead of a bowling ball, it's throwing out superheated gas at thousands of meters per second. And that gas pushing one way means the rocket moves the other way. Here's the thing that makes this so elegant and so important. A rocket doesn't need anything to push against. It doesn't need air. It doesn't need ground. It doesn't need water. It carries its own reaction mass, the stuff it throws out, right there inside itself. And that's why rockets are the only machines we've ever built that can work in the vacuum of space. Jet engines are incredible machines, but they need to gulp in air from the atmosphere to burn their fuel. Propellers push against air. Wheels push against ground. A rocket pushes against nothing but its own exhaust. It's completely self-contained. Think about what that means. It means a rocket is the only engine that can take you from the surface of the Earth to the Moon, to Mars, to Jupiter, to the edge of the solar system and beyond. Nothing else even comes close. But understanding that basic principle and actually building a working rocket, those are two very, very different things, and the gap between them took centuries to close. Let's go way back. The story of rockets starts, as so many engineering stories do, with gunpowder. And gunpowder starts in China, probably sometime around the 9th century. The exact date is fuzzy. Some historians push it earlier, some later. But by roughly 850 AD, Chinese alchemists had stumbled onto a mixture of saltpeter which is potassium nitrate, sulfur, and charcoal, that had this alarming tendency to catch fire and burn very, very fast. Now, these alchemists weren't trying to invent weapons. Many of them were actually searching for an elixir of immortality, which is a wonderful irony when you think about it. They were looking for something to preserve life, and accidentally created one of the most effective tools for ending it. But that's a story for another time. What matters for us is what happened when someone, and we genuinely don't know who, figured out that if you packed this gunpowder mixture into a tube that was sealed at one end and open at the other, and you lit it, the hot gas would come roaring out the open end, and the tube would fly in the opposite direction. The first rockets, they were called fire arrows, and by the 10th and 11th centuries, Chinese military forces were using them in battle. Imagine that. Imagine being a soldier in, say, 1044 AD, and suddenly these screaming, fire-trailing tubes come arcing over the battlefield toward you. You'd never seen anything like it. Nobody had. These early rockets were crude, wildly inaccurate, probably more terrifying than they were lethal, honestly. The gunpowder was inconsistent. The tubes were bamboo or paper, and there was no real way to aim them with any precision. But the principle was there. The engineering was primitive, but the physics was exactly the same physics that would eventually put human beings on the moon. Hot gas goes out one end, the thing moves the other way. Newton's third law, working perfectly, a full 600 years before Newton was even born to write it down. And here's something I love about this part of the story. Knowledge of rockets spread slowly westward along trade routes, the Silk Road, maritime connections, the movement of armies. By the 13th century, there are records of rocket-like weapons being used by Arab forces, and not long after that, the technology shows up in Europe. Roger Bacon, the English friar and early scientist, wrote about gunpowder compositions around 1267. By the late medieval period, rockets were showing up in European warfare, though they were still basically just fireworks strapped to sticks. The engineering hadn't advanced much. The fundamental problem was that nobody really understood why rockets worked. They knew that you lit the powder and the thing flew, but the deeper question, what was actually happening in terms of forces and motion, that required a framework of physics that simply didn't exist yet. Which brings us to Isaac Newton and the year 1687. That's when Newton published the Principia Mathematica, one of the most important books ever written, and in it he laid out his 3 laws of motion. The first law, an object at rest stays at rest, and an object in motion stays in motion unless acted on by an external force. The second law, force equals mass times acceleration. And the third law, the one that matters most for us tonight, for every action there is an equal and opposite reaction. Now, Newton wasn't thinking about rockets when he wrote this. He was trying to describe the fundamental behavior of the universe, why planets orbit, why apples fall, why everything moves the way it does. But buried in that third law is the complete theoretical foundation for rocketry. If you can generate a force in one direction by expelling mass, you will experience an equal force in the opposite direction, period. It doesn't matter if you're in an atmosphere or in a vacuum. It doesn't matter if you're on the ground or in orbit. The law is universal. And yet, and this is the part that always gets me, even after Newton gave us the theoretical tools, it took another 200 years before anyone seriously tried to build a rocket that could do more than just carry a warhead a few hundred meters across a battlefield. 2 centuries. Why? Well, partly because the engineering challenges were enormous, and nobody had the materials or the manufacturing techniques to solve them. But partly, honestly, because the idea of using a rocket to go to space seemed completely insane. It was the stuff of fiction, of fantasy. Serious scientists didn't waste their time on it, but there were exceptions. And the first person who really sat down and worked out the mathematics of space travel using rockets was a Russian school teacher named Konstantin Tsiolkovsky, born in 1857 in a small village in the Russian Empire. Tsiolkovsky had a rough start in life. He contracted scarlet fever as a child and lost most of his hearing, which isolated him socially and, perhaps more importantly, kept him out of the formal academic institutions of his time. He was largely self-taught. He read voraciously, taught himself calculus, devoured the science fiction of Jules Verne, and became absolutely consumed by the idea of spaceflight, not as a fantasy, but as an engineering problem that could actually be solved. And in 1903, the same year the Wright brothers flew at Kitty Hawk, which is a coincidence that never stops being remarkable to me, Tsiolkovsky published a paper called The Exploration of Cosmic Space by Means of Reaction Devices. In it, he derived what we now call the Tsiolkovsky rocket equation. And this equation is so fundamental to rocketry that every single rocket ever built, from a bottle rocket in your backyard to the Saturn V, obeys it. So let's talk about what it says, because it's genuinely beautiful in its simplicity and genuinely terrifying in its implications. The rocket equation tells you how much speed, how much change in velocity, which engineers call delta V, a rocket can achieve based on just 2 things: how fast the exhaust leaves the rocket, and what fraction of the rocket's total mass is propellant versus everything else. That's it. Those are your 2 levers. You can make your exhaust go faster, or you can make a larger percentage of your rocket be fuel. And here's where the terrifying part comes in. The equation is logarithmic. That means the relationship between how much fuel you carry and how much speed you get is not linear. It's not like adding 10% more fuel gives you 10% more speed. The returns diminish savagely. To double your delta V, you don't need twice as much fuel. you need exponentially more. And this is the fundamental tyranny of rocketry. It's the reason rockets are so enormous and yet carry such tiny payloads. It's the reason getting to orbit is so brutally difficult. Think about it this way. To get from the surface of the Earth into low orbit, you need a delta V of roughly 9.5 kilometers per second. That's about 34,000 kilometers per hour. That's absurdly fast. And because of the rocket equation, to achieve that speed with chemical propellants, which is what we've used for almost every rocket ever built, your rocket at liftoff needs to be roughly 90% fuel by mass. 90%. Imagine a soda can that's 90% soda and only 10% aluminum. Now imagine that the aluminum also has to include the engines, the guidance systems, the structural supports, and oh, by the way, the actual payload you're trying to get to space. You're trying to squeeze everything that matters into that last sliver of mass. Tsiolkovsky understood this. He understood it in 1903, sitting in a small house in Kaluga, teaching high school students by day and dreaming about the stars by night. And he didn't just identify the problem, he proposed solutions. He was the first person to seriously suggest using liquid propellants instead of solid gunpowder, because liquid fuels and oxidizers could be fed into a combustion chamber at controlled rates, producing more efficient and more controllable thrust. He proposed multi-stage rockets, the idea that instead of building one giant rocket, you stack smaller rockets on top of each other and throw away each stage as it empties, so you're not wasting energy hauling empty fuel tanks. He even sketched out designs for space stations and described the experience of weightlessness. In 1903, the man was decades ahead of his time, and almost nobody outside Russia paid any attention. But here's what I find most poignant about Tsiolkovsky. He knew he would never build these things himself. He didn't have the resources, the funding, or the institutional support. He was a provincial school teacher with a hearing disability in Tsarist Russia. What he had was the mathematics, the vision, and the patience to write it all down so that someone, someday, could use it. He once wrote something that I think about a lot. He said, "The earth is the cradle of humanity, but mankind cannot stay in the cradle forever." He saw the whole arc of the future, even though he could only contribute to the very first step. Now, while Tsiolkovsky was working out the theory in Russia, completely independently, on the other side of the world, a quiet, stubborn, somewhat eccentric American physicist was about to take the next step, from equations on paper to actual hardware. His name was Robert Goddard, and he was born in 1882 in Worcester, Massachusetts. And if Tsiolkovsky was the dreamer who mapped the theoretical landscape, Goddard was the tinkerer who got his hands dirty, who built things that actually flew, and who was mocked for it in ways that would haunt him for the rest of his life. The story of Robert Goddard is one of the most fascinating and, honestly, one of the saddest stories in the history of engineering, and it starts with a cherry tree in the fall of 1899. Goddard was 17 years old, and one October afternoon he climbed a cherry tree in his backyard to trim some dead branches. And while he was up there, he looked out across the meadows and fields stretching away from him, and something happened. He later described it as a kind of vision, not a religious experience exactly, but a moment of absolute clarity. He imagined a device, some kind of machine, spinning up into the sky, rising toward Mars. And from that moment on, he was consumed. He marked the date, October 19th, 1899, and for the rest of his life, he treated it almost like a private anniversary. Every year on that date, he would pause and reflect on the work he'd done and how far he still had to go. There's something deeply human about that, right? A teenager in a tree, staring at the sky, and the whole trajectory of his life bending in that one quiet moment. Now, Goddard was not like Tsiolkovsky. He wasn't isolated from the scientific establishment. He went to Worcester Polytechnic Institute, then got his PhD in physics from Clark University. He was a trained physicist, a rigorous experimentalist, and he had access to real laboratories. But he shared something crucial with Tsiolkovsky. He arrived at the same fundamental conclusions independently. He worked out that rockets would function in a vacuum, that liquid propellants were far superior to solid ones, and that multi-staging was the key to reaching extreme altitudes. He did this math on his own, without knowing about Tsiolkovsky's work, which was published in Russian in an obscure journal that essentially nobody in the West had read. Two brilliant minds, separated by an ocean and a language barrier, converging on the same truths. That happens more often in the history of science than you might expect. And it's always a little eerie when it does. But here's where Goddard diverged from Tsiolkovsky in the most important way. He didn't just theorize, he built things. And the first thing he needed to figure out was whether a rocket nozzle could actually be made efficient enough to be practical. See, the raw principle is simple. Throw stuff out the back, go forward. But the engineering reality is brutal. If you just let hot gas escape through a hole, you waste an enormous amount of energy. The gas expands chaotically, shoots out in all directions, and most of its potential thrust is lost. What you need is a way to channel that expanding gas, to shape it, to accelerate it in a controlled direction. And this is where we need to talk about something called a de Laval nozzle, which is one of those engineering inventions that seems almost too elegant to be real. The de Laval nozzle was actually invented in the 1880s by a Swedish engineer named Gustaf de Laval, and he designed it for steam turbines, not rockets. But the physics is universal. Here's how it works, and I want you to picture this because it's genuinely beautiful in its simplicity. Imagine a tube that starts wide, then narrows to a tight throat, a pinch point, and then flares wide again on the other side. So it's like an hourglass shape, or a waist. Hot, high-pressure gas enters the wide end, gets squeezed through the narrow throat, and then expands into the widening section on the other side. Now, here's the counterintuitive part. You might think that squeezing gas through a narrow opening and then letting it expand would slow it down, the way water slows when a river widens. But gas doesn't behave like an incompressible liquid. When a gas is moving at subsonic speeds and you squeeze it through a narrower channel, it speeds up. That part is intuitive, like putting your thumb over a garden hose. But once the gas reaches the speed of sound at the throat, something remarkable happens. In the expanding section after the throat, the gas actually continues to accelerate. It goes supersonic. The widening of the nozzle after the throat allows the gas to expand and convert its thermal energy, its heat and pressure, into kinetic energy, into raw velocity. Think about what that means. You're taking hot, high-pressure gas that's barely moving and converting it into a narrow, focused jet moving at thousands of meters per second. And the faster your exhaust moves, the more thrust you get per kilogram of propellant. That's the direct connection to Tsiolkovsky's rocket equation. Remember, the exhaust velocity is the key variable that determines how efficient your rocket is. A better nozzle means higher exhaust velocity, which means you need less fuel, which means you can go farther. The de Laval nozzle is arguably the single most important piece of hardware in all of rocketry, and every rocket engine ever built, from Goddard's tiny prototypes to the Saturn V to the engines on a SpaceX Falcon 9, uses some version of this converging, diverging nozzle shape. It's one of those things where once you understand it, you start seeing it everywhere. Goddard understood this. He ran experiments in his laboratory at Clark University, testing different nozzle designs, measuring how much of the propellant's energy could be converted into directed thrust. And in 1919, he published a paper through the Smithsonian Institution called A Method of Reaching Extreme Altitudes. It's a modest title for what was really a revolutionary document. In it, he laid out the mathematics of rocket propulsion, described his experimental results showing that rockets could work in a vacuum. He'd actually tested this by firing small rockets inside evacuated chambers, and he proposed that a rocket could theoretically be sent to the moon. He even suggested, almost as an afterthought, that a rocket carrying a payload of flash powder could be crashed into the lunar surface and the resulting flash observed through telescopes, proving the rocket had arrived. And this is where things went wrong for Goddard, in a way that would shape the rest of his career. The press got hold of the paper, and they fixated on the moon part. On January 12, 1920, the New York Times ran an editorial mocking Goddard. The editorial said he lacked the knowledge ladled out daily in high schools, because he apparently didn't understand that a rocket couldn't work in a vacuum. There was nothing to push against. Now, this is wrong. This is flatly, completely, embarrassingly wrong. The New York Times editorial board was making exactly the mistake that confuses people about Newton's third law. The rocket doesn't push against the air. It pushes against its own exhaust. The reaction mass carries the momentum. Goddard knew this. He had proven it experimentally, but the damage was done. He became a figure of public ridicule. Moon Man, the professor who wanted to shoot rockets at the moon, and Goddard, who was already a private and somewhat prickly person, retreated further into secrecy. He became almost pathologically secretive about his work, refusing to publish results, refusing to share data, working in isolation. And that secrecy, born from humiliation, would end up being one of the great tragedies of early rocketry, because it meant that the knowledge Goddard was accumulating, hard-won, practical engineering knowledge about how to actually build and fly liquid-fueled rockets, stayed locked up in his notebooks instead of advancing the field. But let's not get ahead of ourselves. Let's talk about what he actually built, because this is the good part. Through the early 1920s, Goddard was working on the problem of liquid-fueled rocket engines. And this is a much harder problem than it might sound. With a solid-fuel rocket, like the ones the Chinese invented 1,000 years ago, you basically light a tube of propellant and stand back. The fuel and the oxidizer are already mixed together in the solid grain, and the burn is relatively simple to manage. But a liquid-fueled rocket is a completely different beast. You have two separate liquids, a fuel and an oxidizer, stored in separate tanks, and you need to pump them into a combustion chamber, mix them in the right proportions, ignite them, sustain a stable combustion process at extreme temperatures and pressures, and direct the resulting exhaust through your nozzle. Every one of those steps is an engineering nightmare. Think about the combustion chamber alone. You're burning propellant at temperatures that can exceed 3,000 degrees, hot enough to melt through virtually any metal you could build the chamber out of. So how do you contain a fire that's hotter than the melting point of its container? This is a problem that would plague rocket engineers for decades, and Goddard was the first person to seriously wrestle with it. He tried different approaches, using refractory materials, designing chambers that could be replaced after each firing, experimenting with ways to cool the chamber walls. He eventually hit on the idea of regenerative cooling, where you route one of the cold liquid propellants, usually the fuel, through channels in the chamber walls before injecting it into the combustion zone. The cold liquid absorbs heat from the walls, keeping them from melting, and in the process the fuel gets preheated, which actually makes combustion more efficient. It's a beautiful piece of engineering logic, using the problem to solve itself. On March 16, 1926, in a snow-covered field on his Aunt Effie's farm in Auburn, Massachusetts, Robert Goddard launched the world's first liquid-fueled rocket. It was tiny, about 10 feet tall, with the combustion chamber and nozzle mounted at the top, above the fuel tanks, in an arrangement that looks almost comical by modern standards. The flight lasted about 2.5 seconds. The rocket rose 41 feet into the air and landed 184 feet away in a cabbage patch. The whole thing was over almost before it began, but think about what had just happened. For the first time in human history, a vehicle powered by liquid propellants had left the ground under its own thrust. Every liquid-fueled rocket that has ever flown since, every Atlas, every Soyuz, every space shuttle main engine, every Raptor engine, traces its lineage back to that spindly little device rising out of a Massachusetts cabbage field on a cold March afternoon. Goddard kept working. He moved his operations to Roswell, New Mexico. Yes, that Roswell, decades before it became famous for entirely different reasons, because he needed the open space and the clear weather. With funding from the Guggenheim family, arranged through the aviator Charles Lindbergh, who had taken a personal interest in Goddard's work, he built increasingly sophisticated rockets through the 1930s. His rockets reached altitudes of nearly 2 kilometers. He developed gyroscopic stabilization systems to keep them flying straight. He built turbopumps to feed propellant into the combustion chamber at high pressure. He patented vane-based thrust vector control, little deflectors in the exhaust stream that could steer the rocket by redirecting the thrust. Nearly every major subsystem of a modern rocket engine, Goddard either invented or prototyped first, and yet he worked in almost total isolation. He published almost nothing. When other researchers wrote to him asking about his methods, he either ignored them or gave vague, unhelpful answers. He was terrified of being scooped, of having his ideas stolen, and so the knowledge stayed with him in his workshop in the New Mexico desert, while across the Atlantic, a group of young German engineers were about to take rocketry in a direction that Goddard could never have imagined, not because they were smarter than him, but because they had something he never had. They had the full backing of a nation-state, with essentially unlimited funding, thousands of workers, and a terrifying motivation. The story of how rocketry moved from a one-man operation in a cabbage patch to the most expensive weapons program in human history is one of the strangest and most morally complicated chapters in the history of technology, and it centers on a young aristocrat with movie star looks and a childhood dream of spaceflight, who made a deal with the devil to make that dream come true. His name was Wernher von Braun, and he was born in 1912 in Virsitz, in what was then the German Empire, to a wealthy, titled family. His father was a baron, a conservative politician who would later serve as a minister in the Weimar Republic. His mother was a woman of considerable education and curiosity, and she gave the young Wernher a telescope for his confirmation, a gift that by his own account changed the direction of his life. He became obsessed with the idea of space travel, not rockets as weapons, not rockets as scientific instruments, but rockets as vehicles to carry human beings off this planet and to the moon, to Mars, to wherever they could reach. That dream never left him. It was the fixed star around which everything else in his life orbited, and it's the key to understanding both his brilliance and his moral catastrophe. As a teenager, von Braun got his hands on a copy of Hermann Oberth's book, The Rocket into Interplanetary Space, published in 1923. Oberth was a Romanian-born German physicist who had independently arrived at many of the same conclusions as Tsiolkovsky and Goddard: liquid propellants, multi-staging, the mathematics of escape velocity. And, unlike Goddard, Oberth published openly and enthusiastically. His book was rigorous but accessible, and it electrified a generation of young Germans who were already primed for this kind of dreaming. Von Braun later said that when he first read Oberth's book, he couldn't follow the mathematics, so he threw himself into studying calculus and physics specifically so he could understand it. That tells you something about the intensity of his motivation. By the late 1920s, Germany had a thriving amateur rocketry scene. There was a group called the Verein für Raumschifffahrt, the Society for Space Travel, and it included Oberth himself, along with dozens of enthusiastic young engineers and tinkerers who were building small liquid-fueled rockets on a shoestring budget at an abandoned ammunition dump in the suburbs of Berlin that they called the Raketenflugplatz, the rocket airport. Von Braun joined them as a teenager, and he was good. He was charismatic, technically sharp, and here's what really mattered: he was an extraordinary organizer. He could get people to work together, to believe in a shared vision, to keep going when the rockets kept blowing up on the test stand. Now, here's where the story takes its dark turn. The German military had been watching these amateur rocketeers with quiet interest. The Treaty of Versailles, which ended the First World War, had placed strict limits on Germany's artillery, the range and caliber of guns they could build. But the treaty said nothing about rockets, because in 1919, military rockets were barely a concept. The German Army's Ordnance Department, under a captain named Walter Dornberger, realized that rockets represented a loophole, a legal path to long-range weapons that the treaty couldn't touch. And so in 1932, they came to the Amateur Rocket Club with an offer: funding, facilities, resources. The catch was that the work would be military and it would be secret. Most of the amateurs walked away. They didn't want to build weapons, but von Braun said yes. He was 20 years old, and he saw this as the only realistic path to building rockets large enough to eventually reach space. He would later frame this decision as purely pragmatic. He needed money and infrastructure that no civilian institution could provide, and the military had both. Whether that justification holds up morally is something people have debated ever since, and we'll come back to it. But the immediate consequence was that von Braun became, essentially, the technical leader of the German Army's rocket program, and he threw himself into it with everything he had. They started at a small facility at Kummersdorf, south of Berlin, where von Braun and a growing team began building and testing liquid-fueled rocket engines. The early work was dangerous and chaotic. Engines exploding, propellant lines rupturing, test stands catching fire. But they learned fast. Von Braun earned his doctorate in physics in 1934 at the age of 22, and his dissertation was on liquid rocket propulsion. The dissertation itself was classified by the military, which tells you how deeply intertwined his academic work and his weapons work had already become. By 1936, the program had outgrown Kummersdorf, and they moved to a new, purpose-built facility on the Baltic coast at a place called Peenemünde. And this is where the story shifts from a small research program to something unprecedented in the history of engineering. Peenemünde became, in effect, the world's first large-scale rocket development center. At its peak, it employed thousands of engineers, technicians, and support staff. It had wind tunnels, engine test stands, a liquid oxygen production plant, launch pads, and a manufacturing facility. The scale of investment was staggering. The German government poured resources into Peenemünde that rivaled what they spent on any other single weapons program. The goal was a ballistic missile that could carry a 1-ton warhead over a distance of about 300 kilometers. They called it the A4, Aggregate 4, though the world would come to know it by its propaganda name, the V2, the Vergeltungswaffe 2, the Vengeance Weapon 2, and building it required solving essentially every major problem in rocketry simultaneously. Think about what they were attempting: a vehicle that had to accelerate to roughly 5 times the speed of sound, climb to the edge of space, arc over on a ballistic trajectory, and hit a target hundreds of kilometers away, all with 1940s technology, no computers to speak of, and materials science that was still in its infancy. Let's talk about how the V2 actually worked, because it's a remarkable piece of engineering regardless of what it was designed to do. The rocket stood about 14 meters tall and weighed around 12.5 metric tons at launch, most of that weight being propellant. It burned ethanol, regular grain alcohol, diluted with water, and liquid oxygen. The choice of ethanol was partly practical and partly strategic. Germany had limited access to petroleum, but they could produce ethanol from potatoes. You fight a war with the chemistry you have. The engine, the heart of the thing, produced about 25 tons of thrust. Now, remember how we talked about the de Laval nozzle, that converging, diverging shape that accelerates the exhaust gases to supersonic speeds? The V2's engine used exactly that principle, scaled up enormously. The combustion chamber was where the ethanol and liquid oxygen were injected, mixed, and ignited, producing gases at temperatures around 2,700 degrees Celsius. Those gases then accelerated through the nozzle throat and out the expanding bell, reaching exhaust velocities of roughly 2 kilometers per second. But here's one of the huge engineering challenges they faced. How do you keep a combustion chamber from melting when the gases inside it are hot enough to soften steel? Goddard had pioneered regenerative cooling, running the fuel through channels around the outside of the chamber before injecting it, so the fuel absorbs heat and protects the chamber walls. The V2 team used this exact technique. The ethanol flowed through a jacket surrounding the combustion chamber and the upper part of the nozzle, cooling the metal while simultaneously preheating the fuel, which actually made combustion more efficient. It's elegant. You're using the problem, the excess heat, as part of the solution. The propellant delivery system was another marvel. You can't just let liquid oxygen and ethanol trickle into a combustion chamber that's producing 25 tons of thrust. You need to force them in at enormous flow rates and pressures. The V2 used a turbopump, a high-speed turbine-driven pump that could deliver about 125 liters of propellant per second into the combustion chamber. The turbine itself was powered by steam generated from the decomposition of hydrogen peroxide, using sodium permanganate as a catalyst. So you had this separate little chemical reaction whose only job was to spin a turbine fast enough to shove propellant into the engine at the required rate. It's a system within a system, each piece depending on every other piece working correctly. For guidance, the V2 used a pair of gyroscopes, spinning masses that resist changes in orientation and can therefore sense when the rocket is drifting off course. The gyroscopes fed signals to a simple analog control system that actuated graphite vanes mounted in the exhaust stream, exactly the kind of thrust vector control that Goddard had patented years earlier. When the rocket needed to turn slightly to the right, the vanes would deflect the exhaust slightly to the left, pushing the tail of the rocket to the right. It's Newton's third law again, applied with precision in a stream of gas moving at 2 kilometers per second. The V2 also had aerodynamic fins for stability during the portion of flight within the atmosphere, but the vanes in the exhaust were what really steered it. The first successful test flight of the A4 happened on October 3rd, 1942. The rocket climbed to an altitude of about 84 kilometers, the edge of space by most definitions, and traveled roughly 190 kilometers downrange. Dornberger, who had been championing the program for a decade, reportedly said that evening, "Today the spaceship was born." And in a purely technical sense, he was right. This was the first human-made object to reach the boundary of space. It was a genuine milestone in the history of technology, but what it was born to do was kill people. And here's where the story becomes something you have to sit with, because there's no way to separate the engineering achievement from the human cost. The V2 was deployed operationally starting in September 1944, primarily against London and Antwerp. Over 3,000 V2s were launched in combat. They traveled faster than the speed of sound, which meant you couldn't hear them coming. There was no warning, no air raid siren, no time to take shelter. One moment, everything was normal, and the next moment, a building was gone. The missiles killed an estimated 9,000 civilians in the target cities. But here's the thing that makes the V2 story truly horrifying, and it's a detail that doesn't get mentioned enough. More people died building the V2 than were killed by it. The rockets were manufactured in an underground factory called the Mittelwerk, carved into the Harz Mountains, using slave labor from the Mittelbau Dora concentration camp. Prisoners, many of them political prisoners, resistance fighters, prisoners of war, were worked to death in appalling conditions. They labored in tunnels with inadequate ventilation, breathing rock dust and toxic fumes, sleeping in the tunnels themselves during the early months before barracks were built. Thousands died from exhaustion, disease, starvation, and deliberate brutality. The estimates vary, but roughly 12,000 forced laborers died in the production of the V2. 12,000 people to build a weapon that killed 9,000. Von Braun knew about this. The degree of his personal involvement and awareness has been debated, but he visited the Mittelwerk multiple times. He was a member of the SS. He later claimed he was pressured into joining and that it was essentially ceremonial, but he held the rank of Sturmbannführer, equivalent to a major. After the war, he consistently minimized his knowledge of the labor conditions and his complicity in the system that produced them. It's a stain that no amount of later achievement can erase, and it's important to say that plainly. And yet the engineering knowledge that came out of the V2 program was real, and it became the foundation for essentially everything that followed in rocketry, on both sides of the Iron Curtain. Because as the war ended in the spring of 1945, with Allied forces closing in from the west and Soviet forces from the east, there was a frantic scramble to capture not just the rockets themselves, but the engineers who had built them and the documentation that explained how. The Americans launched an operation called Project Paperclip, specifically designed to recruit German rocket scientists before the Soviets could get to them. Von Braun, who had always been more afraid of the Soviets than the Americans, deliberately moved his team westward and surrendered to American forces in May 1945. He and about 120 of his key engineers were brought to the United States, along with enough V2 components to assemble roughly 100 rockets. The Soviets, meanwhile, captured Peenemünde itself, the Mittelwerk factory, and a number of German engineers who hadn't managed to flee west. They also captured extensive technical documentation and, crucially, they had their own brilliant rocket engineer who would take what the Germans had built and push it further than anyone thought possible. His name was Sergei Korolev, and his story is, if anything, even more extraordinary than von Braun's, because Korolev had spent 6 years in the Soviet Gulag, nearly dying in a gold mine in Kolyma, one of the most brutal camps in the entire system, before being pulled out and put to work designing weapons for the same government that had tried to kill him. Think about that for a second. The man who would become the most important figure in the Soviet space program, the person who put the first satellite in orbit, the first human in space, the architect of an entire nation's rocket capability, that man had been arrested, beaten, had his jaw broken during interrogation, was sentenced to hard labor, and was sent to a place where the average life expectancy was measured in months. And when his country decided it needed him again, it didn't apologize. It just pulled him out of the camp, dusted him off, and said, "Get back to work." Korolev's story starts in 1907 in the Ukrainian city of Zhytomyr. His childhood was difficult. His parents separated when he was young, and he was raised largely by his grandparents. But like Goddard, like von Braun, he caught the spaceflight bug early. By his teenage years, he was already building gliders, and he enrolled in the Kiev Polytechnic Institute before transferring to the Bauman Moscow State Technical University, which was one of the premier engineering schools in the Soviet Union. He was brilliant, driven, and charismatic in a blunt, forceful kind of way. People who worked with him later described him as a man of enormous willpower, the kind of person who could drag an entire project forward through sheer determination. In the early 1930s, Korolev was part of a group called GERD, the Group for the Study of Reactive Motion, which was essentially the Soviet equivalent of the Verein für Raumschifffahrt that von Braun had joined in Germany. They were building small liquid-fueled rockets, experimenting with different propellant combinations, learning the same hard lessons about combustion instability and cooling and pump design that everyone else was struggling with. Korolev rose quickly, becoming one of the leaders of the Soviet rocket development effort. By the mid-1930s, he was working on rocket-powered aircraft and guided missiles, doing genuinely cutting-edge work. And then, in 1938, Stalin's Great Purge reached him. Korolev was arrested on June 27th, accused of being a member of an anti-Soviet counter-revolutionary organization, a charge that was, as far as anyone can tell, completely fabricated. During his interrogation, he was beaten so severely that his jaw was broken and never healed properly. He was sentenced to 10 years of hard labor. First, he was sent to a transit camp, then to Kolyma in the far northeast of Siberia, where winter temperatures drop to -50 degrees Celsius, and prisoners worked in gold mines under conditions that killed thousands. Korolev contracted scurvy. He lost most of his teeth. He was, by multiple accounts, very close to death when a combination of luck and bureaucratic intervention got him transferred out of Kolyma and eventually into what the Soviets called a sharashka, a prison laboratory where scientists and engineers were forced to work on military projects while still technically serving their sentences. It was a prison, but it was a prison with a drafting table instead of a pickaxe, and it probably saved his life. He spent the war years in these Sharashkas, working on rocket-assisted aircraft alongside other imprisoned engineers, including the famous aircraft designer Andrei Tupolev, who had also been swept up in the purges. Korolev was released in 1944, but not fully rehabilitated, meaning the conviction still stood. The stain was still on his record. He was a free man in name, but he carried the psychological and physical scars of 6 years in the camps for the rest of his life. So when the war ended and the Soviets captured V-2 technology from Germany, it was Korolev they turned to. He was sent to Germany in 1945 to study what the Germans had built, to interview the remaining engineers, to understand every detail of the V-2. And here's the thing, Korolev was both impressed and frustrated. Impressed because the V-2 was genuinely the most advanced rocket in the world, far ahead of anything the Soviets had built. Frustrated because he knew that many of the underlying ideas, liquid propellants, regenerative cooling, gyroscopic guidance, were things he and his colleagues had been working on before the purges had destroyed their program. If Stalin hadn't arrested half the Soviet Union's rocket engineers in 1938, they might have been further along than the Germans. That's one of the great tragic what-ifs of engineering history. But Korolev was nothing if not pragmatic. He took what the Germans had built and he learned from it. The Soviets began by essentially reverse engineering the V-2, building their own copies called the R-1, which flew in 1948. But Korolev wasn't interested in just copying. He wanted to go further, and this is where the story of rocketry becomes inseparable from the story of the Cold War. Because the reason Korolev got essentially unlimited resources wasn't spaceflight, it was nuclear weapons delivery. Here's the strategic problem the Soviet Union faced in the late 1940s. They had tested their first atomic bomb in 1949, much sooner than the Americans expected, partly thanks to espionage. But having a bomb and being able to deliver it to a target on another continent are two very different problems. The Americans had long-range bombers, the B-29, and later the B-52, that could reach the Soviet Union from bases in Europe and Asia. The Soviets didn't have equivalent bomber capability to reach the continental United States, and their early nuclear weapons were heavy, much heavier than the American ones. The first Soviet thermonuclear weapon weighed several tons. You couldn't just strap it under the wing of any airplane, so the Soviet military needed a delivery vehicle that could carry a very heavy warhead across intercontinental distances, and rockets were the answer. This is what gave Korolev his opening. He proposed building an intercontinental ballistic missile, an ICBM, capable of carrying a nuclear warhead from Soviet territory to the United States. The project was approved, and it became the R-7. Now, the R-7 is one of the most remarkable rockets ever built, and its basic design is still flying today, which is just extraordinary when you think about it. The rocket that launches Soyuz missions to the International Space Station in the 21st century is a direct descendant of a missile that Korolev designed in the early 1950s. Let's talk about how it works, because the engineering is fascinating and it solved several problems in a very clever way. The fundamental challenge was thrust, to lift a heavy nuclear warhead and enough propellant to reach intercontinental range. Korolev needed far more thrust than a single V2 engine could provide. The V2's engine produced about 25 tons of thrust. Korolev needed something like 20 times that. Now, you might think the obvious solution is to just build a much bigger engine, and that's partly what he did. His team, led by the engine designer Valentin Glushko, developed a new engine called the RD-108 for the core stage and the RD-107 for the boosters. But here's the clever part. Instead of trying to build one enormous engine, Korolev used a configuration that's sometimes called a cluster or a packet design. The R7 had a central core stage surrounded by 4 strap-on boosters, each of which was essentially a separate rocket with its own engines and propellant tanks. All 5 units ignited on the ground at launch, and about 2 minutes into the Faran flight, when the 4 boosters had burned through their propellant, they separated and fell away, leaving the lighter central core to continue on its own. Think about what this achieves. You get the benefit of staging, shedding dead weight as you go, just like Tsiolkovsky described. But you don't have the problem of igniting an upper stage engine in flight, which was still a tricky and unreliable process in the 1950s. Everything lights up on the ground, where you can verify it's working before you commit to launch. If one of the boosters doesn't ignite properly, you can shut everything down and fix the problem. It's an elegant solution to a very real engineering risk. Each RD-107 booster engine actually had 4 combustion chambers sharing a single turbopump. So when people count the engines on an R7, the numbers can get confusing. The 4 boosters had 4 chambers each. The core had 4 chambers plus, and there were smaller vernier engines for steering. In total, you had 32 combustion chambers firing at liftoff. The combined thrust was around 400 tons, which was absolutely enormous for its time. The propellants were liquid oxygen and kerosene, specifically RP1, a refined form of kerosene that burns cleanly and has good energy density. This was a step up from the V2's ethanol, giving better performance. And here's something worth pausing on. The choice of kerosene over ethanol matters more than it might seem. Remember, the energy you get out of a rocket depends on exhaust velocity, and exhaust velocity depends on the energy released per unit mass of propellant and how efficiently your nozzle converts that thermal energy into directed kinetic energy. Kerosene is a denser fuel than ethanol and releases more energy per kilogram When burned with oxygen, that means higher exhaust velocity, which means better specific impulse, the measure of how efficiently a rocket uses its propellant. The R-7's engines achieved a specific impulse of around 310 seconds at sea level, compared to the V-2's roughly 200 seconds. That's a massive improvement, and it comes from better propellants, better combustion chamber design, and better nozzle engineering. Glushko's engines were masterpieces of practical engineering. The combustion chambers operated at much higher pressures than the V-2's, which improved efficiency but also created enormous challenges. Higher pressure means higher temperatures, more stress on the chamber walls, more violent combustion dynamics. The cooling problem becomes even more severe. Glushko used regenerative cooling, the same principle Goddard had invented, but pushed it much further, routing the kerosene fuel through channels in the chamber walls before injecting it into the combustion chamber. The fuel absorbed heat from the walls, keeping them from melting, and arrived in the chamber preheated, which actually improved combustion efficiency. It's a beautiful piece of engineering where solving one problem, cooling, simultaneously helps with another problem, combustion efficiency. The R-7 first flew successfully on August 21st, 1957, traveling about 6,000 kilometers from the launch site at Baikonur in Kazakhstan to the Kamchatka Peninsula in the Far East. As a missile, it was actually somewhat impractical. It took hours to fuel and prepare. It couldn't be kept ready to launch on short notice, and the launch facilities were enormous and vulnerable. But Korolev had always had his eye on something beyond weapons delivery. He had been dreaming of space since he was a young man building gliders in Ukraine, and he knew that the R-7 had enough power to put an object into orbit around the Earth. He lobbied the Soviet government relentlessly, arguing that launching a satellite would be a tremendous propaganda victory. The Americans had already announced their intention to launch a satellite as part of the International Geophysical Year, and Korolev argued that beating them would demonstrate Soviet technological superiority to the entire world. The government gave him permission, almost as an afterthought. They didn't fully grasp how significant it would be. On October 4th, 1957, an R-7 rocket launched from Baikonur, carrying a small aluminum sphere, 58 centimeters in diameter, weighing 83.6 kilograms, equipped with nothing but a radio transmitter and some batteries. Sputnik. The word means traveling companion in Russian, and when that little sphere reached orbit and began transmitting its steady beep, beep, beep signal, audible to anyone on Earth with a shortwave radio, the world changed, not because the satellite itself did anything particularly useful. It just beeped, but because the fact that it was up there, circling the planet every 96 minutes, meant that the Soviets had a rocket powerful enough to deliver a nuclear warhead to any point on Earth. The psychological impact was enormous, especially in the United States, where the public reaction bordered on panic. And Korolev wasn't done. Just a month later, on November 3rd, he launched Sputnik 2, carrying a dog named Laika, the first living creature to orbit the Earth. Laika didn't survive the mission. The thermal control system failed, and she died from overheating within hours of reaching orbit, a fact the Soviets didn't fully acknowledge for decades. But the engineering achievement was real, and it demonstrated that a living organism could at least survive the launch and reach orbit, which was a necessary step toward sending a human being up there. And that's exactly where Korolev's mind was already racing. Even before Laika's capsule had completed its first orbit, he was sketching plans for a spacecraft that could carry a person. Not someday, soon, because Korolev understood something about the space race that a lot of people around him didn't. Momentum mattered. Every first was a headline, and every headline was leverage. Leverage to get more funding, more engineers, more freedom to pursue the missions he actually cared about. And the mission he cared about most, the one he'd dreamed about since he was a teenager building gliders in Ukraine, was getting a human being off this planet. But here's the thing about sending a person into space. It's not just a matter of having a big enough rocket. You need to solve a whole cascade of engineering problems that don't exist when you're just lobbing a metal ball into orbit. You need life support, oxygen to breathe, carbon dioxide scrubbed from the air, temperature held within a narrow range that won't cook or freeze your passenger. You need a way to bring them back. That's the really hard part. Getting to orbit is violent and fast, but at least it's a known quantity by this point. Coming back means slamming into the atmosphere at something like 28,000 kilometers per hour and converting all that kinetic energy into heat without killing the person inside. You need a heat shield that can handle temperatures north of 1,500 degrees Celsius. You need a capsule shaped so that it creates the right kind of aerodynamic drag to slow down gradually rather than all at once, because decelerating too fast will kill you just as dead as burning up will. You need parachutes that deploy at exactly the right altitude and speed. You need a way for the cosmonaut or astronaut, depending on which side of the Iron Curtain you're on, to survive the G-forces of both launch and re-entry, which means careful attention to the orientation of the human body relative to the direction of acceleration, because humans can tolerate much higher G loads when the force pushes you into your seat, chest to back, than when it pushes blood away from your brain. Korolev and his team worked through all of these problems with remarkable speed. The spacecraft they designed was called Vostok, which means east in Russian, and its design was elegant in a very Soviet way, robust, simple where it could be, and built with generous margins because they knew there would be things they hadn't anticipated. The capsule itself was a sphere, about 2.3 meters in diameter. Now, that's an interesting design choice. The Americans, when they got around to building their Mercury capsule, went with a cone shape, a blunt body design based on research by a brilliant NASA engineer named Harvey Allen, who'd figured out that a blunt shape actually handles re-entry heating better than a pointy one because it creates a strong bow shock wave that keeps the hottest gases away from the vehicle's surface. But Korolev chose a sphere, and the reason was clever. A sphere is inherently stable during re-entry regardless of its orientation. It doesn't matter which way it's pointing. The aerodynamic properties are the same in every direction. That meant even if the orientation system failed, the capsule would still survive re-entry. It was a design choice driven by the acknowledgement that things go wrong, and when things go wrong in space, you want your spacecraft to be as forgiving as possible. The heat shield was ablative, meaning it was designed to burn away, to char and erode in a controlled fashion, carrying heat away from the capsule as the material vaporized. Think of it like sweating. Your body cools itself by letting water evaporate from your skin, and each molecule of water that evaporates carries energy away with it. An ablative heat shield works on the same principle, except instead of water, you're vaporizing layers of resin-impregnated material at extreme temperatures. The beauty of ablative shielding is that it's self-regulating. The hotter it gets, the faster it ablates, the more heat it carries away, and it doesn't require any moving parts or active systems. It just works, passively, by the physics of phase change and mass transfer. This was technology that both the Americans and Soviets developed more or less independently, drawing on research into ballistic missile warhead re-entry that had been going on throughout the 1950s. Because remember, the whole reason these rockets existed in the first place was to deliver nuclear weapons, and a nuclear warhead has to survive re-entry too. The Vostok spacecraft sat on top of a service module that contained the retro rocket, the engine that would fire to slow the spacecraft down and begin the deorbit process. Here's how orbital mechanics works in this context, and it's beautifully counterintuitive. To come back to Earth from orbit, you don't point your rocket at the ground and fire. You actually fire your engine backward, against your direction of travel, to slow yourself down. This lowers your orbit on the opposite side of the Earth, and as your orbit dips into the upper atmosphere, air resistance does the rest. You're essentially converting a circular orbit into an elliptical one, whose lowest point intersects the atmosphere. It's like, imagine you're swinging a ball on a string in a horizontal circle above your head. If you could somehow slow the ball down just a little at one point in its circle, it would dip lower on the opposite side. Same idea, except the string is gravity and the circle is your orbit. Korolev tested the Vostok design with a series of unmanned flights, some carrying dogs, some carrying mannequins. The Soviets actually dressed the mannequins in spacesuits and called them Ivan Ivanovich, which is basically the Russian equivalent of John Doe. They, needed to test every system: the launch escape system, the heat shield, the parachute deployment, the ejection seat. Yes, ejection seat. In the Vostok design, the cosmonaut didn't actually land inside the capsule. The capsule came down under its own parachute, but it was coming down too fast for a safe landing with a person inside. The Soviets hadn't yet perfected the retro-rocket landing system that later Soyuz capsules would use, so the cosmonaut would eject from the capsule at about 7,000 meters altitude and parachute down separately. This was actually a point of controversy later, because the Fédération Aéronautique Internationale, the international body that certifies aviation and spaceflight records, initially required that a pilot land with their craft for the flight to count as a record. The Soviets kept the ejection detail secret for years to avoid having the record challenged. And then came April 12, 1961. Yuri Gagarin, a 27-year-old fighter pilot from a small town west of Moscow, climbed into Vostok 1 at the Baikonur Cosmodrome. He was chosen from a group of 20 candidates, and the selection criteria tell you a lot about the engineering constraints. He was short, about 5'2", which mattered because the Vostok capsule was tiny. He was calm under pressure, personable, came from a working-class background that would play well for Soviet propaganda, and he had an infectious smile that would photograph well. The flight was almost entirely automated. Gagarin had manual controls available, but they were locked behind a coded panel. The thinking was that in the unknown environment of weightlessness, a cosmonaut might become disoriented or even psychologically impaired. Nobody knew for sure, so the ground controllers wanted to maintain authority. They did give Gagarin the code in a sealed envelope, just in case. The launch went smoothly. The R-7, the same basic rocket design that had launched Sputnik, now refined and human-rated, performed beautifully. Gagarin's famous exclamation as the rocket lifted off was "Poyakali," let's go, and within minutes he was in orbit, the first human being to see the Earth from space. He completed one orbit in 108 minutes. During the flight, he reported that weightlessness was not unpleasant, that he could eat and drink normally, that his vision and thinking were unimpaired. These were genuine unknowns at the time. Serious medical researchers had worried that the human vestibular system might completely malfunction without gravity, or that the heart might not pump blood effectively, or that swallowing might be impossible. Gagarin proved them wrong simply by existing in orbit and reporting back. The re-entry was not entirely smooth, though. When the service module separated from the capsule, a bundle of wires didn't disconnect cleanly, and the two modules remained tethered together for about 10 minutes, causing the capsule to tumble wildly. Gagarin experienced violent oscillations and significant G-forces. Reports suggest up to 8 Gs before the wires finally burned through in the heat of re-entry and the capsule stabilized. He ejected as planned at 7,000 meters and parachuted safely to a field near the Volga River, where he was found by a farmer and her daughter, who were initially alarmed by the sight of a man in a bright orange suit descending from the sky. He reportedly told them, "Don't be afraid. I am a Soviet citizen, like you, who has descended from space, and I must find a telephone to call Moscow." The world reacted with astonishment, and in the United States, the reaction was something closer to alarm, because this was the second time, first Sputnik, now this, that the Soviets had achieved a dramatic space first, and it was becoming clear that the American space program was falling behind. The Americans had their own program, Project Mercury, but it wasn't ready yet. Alan Shepard wouldn't make his suborbital flight until May 5, 1961, 3 weeks after Gagarin, and it wasn't even an orbital flight, just a 15-minute up and down arc. John Glenn wouldn't orbit the Earth until February 1962, nearly a year after Gagarin. And this is where the space race really ignites, because the political pressure created by Gagarin's flight led directly to one of the most consequential decisions in the history of engineering. On May 25, 1961, just 6 weeks after Gagarin's flight, President John F. Kennedy stood before a joint session of Congress and declared that the United States would land a man on the moon and return him safely to Earth before the end of the decade. Think about what that meant from an engineering standpoint. In May 1961, the total American experience with human spaceflight consisted of one 15-minute suborbital hop. They had not yet put a single person in orbit, and the president was committing the nation to landing on the moon within 8.5 years. The moon is roughly 384,000 kilometers away. Getting there requires a rocket vastly more powerful than anything that existed. Landing on it requires solving problems of navigation, propulsion, and life support that no one had even begun to work on in any serious way. And getting back requires doing most of it again in reverse. It was audacious to the point of seeming reckless, and yet it galvanized an entire engineering effort unlike anything the world had seen before or since. At its peak, the Apollo program employed around 400,000 people and consumed about 4% of the entire federal budget. And the rocket they built to do it, the Saturn V, is still, to this day, the most powerful rocket ever successfully flown. It's worth spending some time with the Saturn V because it represents a kind of pinnacle of chemical rocketry, a machine that pushed the engineering of its era to absolute limits. The Saturn V was the brainchild of Wernher von Braun, who by this time was directing the Marshall Space Flight Center in Huntsville, Alabama. And whatever complicated moral reckoning his history demands, and it demands a serious one, his engineering brilliance was undeniable. The Saturn V stood 110 meters tall, about the height of a 36-story building. Fully fueled, It weighed approximately 2,950 metric tons. It was a 3-stage rocket, and each stage was itself a marvel of engineering that deserves its own attention. The first stage, called the SIC, was built by Boeing at NASA's Michoud Assembly Facility in New Orleans. It was powered by 5 F-1 engines, and the F-1 is one of those engineering achievements that almost defies comprehension when you start looking at the numbers. Each F-1 engine produced roughly 6.7 million newtons of thrust, about 1.5 million pounds of force. 5 of them together generated 33.4 million newtons at liftoff. The fuel was RP-1, which is essentially a highly refined kerosene, and the oxidizer was liquid oxygen, just like the R-7, but at a scale that dwarfed anything that had come before. Each F-1 engine consumed about 2,500 kilograms of propellant per second. That's roughly equivalent to emptying an average swimming pool in about 12 seconds. 5 of them running together. You're looking at something like draining 5 swimming pools every 12 seconds. All of that mass being hurled out the back of the rocket as superheated exhaust gas. The turbopump alone in each F-1 engine produced about 55,000 horsepower. One turbopump. That's more power than a locomotive, and there were 5 of these engines bolted to the bottom of the first stage, all firing simultaneously, shaking the ground for miles around Cape Kennedy when they lit up. And here's the thing about the F-1 that really gets engineers excited even today. It almost didn't work. The engine went through years of development, plagued by a problem called combustion instability. This is one of those quietly terrifying issues in rocket engineering. So let's talk about it for a second. When you're injecting enormous quantities of fuel and oxidizer into a combustion chamber and igniting them, the burning doesn't always happen smoothly. Sometimes pressure waves develop inside the chamber, acoustic oscillations essentially, where the combustion process starts feeding energy into these waves, and they grow. They bounce back and forth, reinforcing themselves, and within milliseconds, the pressure fluctuations can become so violent that they tear the engine apart from the inside. It's like the difference between a campfire and an explosion, except both are happening in a confined space, and the transition from one to the other can happen in a fraction of a second. The F-1 suffered from this problem badly during testing in the early 1960s. Engineers at Rocketdyne, the company building the engine, would run a test and the engine would just destroy itself. The combustion chamber would melt through, or the injector plate would crack. And the maddening thing was that it wasn't predictable. You could run 10 tests and have 8 go fine, and then 2 would fail catastrophically, with no obvious difference in the setup. The instability was chaotic in the mathematical sense. It depended on tiny variations in how the propellants mixed, how the flame front propagated, the exact geometry of the chamber at that particular moment. They tried everything. They redesigned the injector plate. That's the component at the top of the combustion chamber, with hundreds of small holes through which the fuel and oxidizer are sprayed in carefully arranged patterns so they mix and burn evenly. They tried different hole patterns, different sizes, different angles. They added baffles to the injector face, physical copper fins that stuck down into the combustion chamber to break up the acoustic waves before they could build. And here's the really wild part of the testing process. They eventually started deliberately introducing instability to see if the engine could recover. They would place small explosive charges inside the combustion chamber, detonate them while the engine was running to create a sudden pressure spike, and then see if the baffles and injector design could damp out the resulting oscillation before it went catastrophic. They called these bomb tests, and they ran hundreds of them, literally setting off explosives inside a running rocket engine to see if it could take the hit and keep going. It took years, something like 2,000 individual test firings, but they got it to work. By about 1965, the F-1 was reliable enough for flight, and the knowledge gained from solving that combustion instability problem became foundational for every large liquid fuel rocket engine that followed. When NASA tried to build new large engines decades later, they actually went back and studied the F-1 test data because some of that institutional knowledge about combustion dynamics had been lost. So that's the first stage, 5 F-1 engines burning for about 2.5 minutes, pushing the entire Saturn V stack from the launch pad to an altitude of roughly 68 kilometers and a speed of about 2,700 meters per second. Then the first stage separates and falls away into the Atlantic Ocean, and the second stage takes over. The second stage was called the S-2, built by North American Aviation, and it used 5 J-2 engines. Now, the J-2 was a completely different beast from the F-1. It burned liquid hydrogen and liquid oxygen, that high-performance combination we touched on earlier with the specific impulse advantage. Liquid hydrogen is incredibly light, which means you get more velocity per kilogram of propellant expelled. The J-2 engines had a specific impulse of about 421 seconds in vacuum, compared to the F-1's roughly 263 seconds at sea level. That's a massive difference. It's why you use hydrogen for the upper stages once you're out of the thickest part of the atmosphere and you've shed the enormous weight of the first stage. Efficiency matters more than raw thrust, but liquid hydrogen is a nightmare to work with. It has to be stored at -253 degrees Celsius, just 20 degrees above absolute zero. It's the smallest molecule there is, so it leaks through seals that would hold any other fluid. It makes metals brittle. The tanks have to be insulated meticulously, and even then, you're constantly losing hydrogen to boil off. The S-2 stage was essentially a giant thermos bottle, and building it pushed the limits of manufacturing precision. The tank walls were milled down to be as thin as possible to save weight, in some places just a few millimeters thick, and they had to hold cryogenic fluids under pressure while enduring the vibration and acceleration of launch. North American aviation had serious quality control problems early on, and there were times when NASA nearly pulled the contract. The SHMF third stage, the SIVB, built by Douglas Aircraft, used a single J2 engine. And here's something clever about the SIVB. It had to be restartable. The second stage would get the spacecraft into a parking orbit around Earth, and then the SIVB's single J2 would fire again to perform what's called the translunar injection burn, the push that sent the Apollo spacecraft out of Earth orbit and on its way to the Moon. Restarting a rocket engine in the weightlessness of orbit is tricky because the propellants are floating around randomly inside the tanks. You need to settle them to the bottom before you can feed them reliably into the turbopumps. The SIVB used small auxiliary thrusters called ullage motors that would fire briefly to create just enough acceleration to push the propellants to the back of the tanks, and then the J2 could restart. Think about the whole sequence for a moment. You've got this 110-meter tower on the launch pad, and in about 12 minutes, 3 stages fire in succession, each one optimized for its part of the journey. Raw thrust to get off the ground, efficient hydrogen propulsion to reach orbit, and then a precisely timed restart to leave Earth behind entirely. The staging principle that Tsiolkovsky wrote about in his apartment in Kaluga in 1903, the one we talked about earlier, this was its ultimate expression. Each stage is discarded when empty, and the remaining rocket gets lighter and more efficient as it goes. The Saturn V's payload to the Moon was about 48,600 kilograms. The Apollo spacecraft itself, with its command module, service module, and lunar module, that's roughly 1.6% of the total launch mass. Everything else, 98.4% of that enormous rocket, was structure and propellant that got thrown away along the way. The tyranny of the rocket equation made physical, and the guidance system deserves a mention too, because getting to the Moon isn't just about raw power, it's about precision. The Saturn V used an instrument unit, a ring-shaped section that sat on top of the S5B stage, packed with electronics. The primary guidance computer was built by IBM and used a stabilized platform with gyroscopes and accelerometers to track the rocket's position and velocity. This was the 1960s, remember? The computing power available was laughably small by today's standards. The guidance computer had about 200 kilobytes of memory. Your phone has something like 1 million times more. But it was enough, because the programmers were extraordinarily careful, and the math was well understood. Orbital mechanics is Newtonian physics. It's deterministic, it's precise, and if you know your current position and velocity accurately enough, you can calculate exactly what burn to perform to reach any point in the solar system. The first unmanned test flight of the Saturn V was Apollo 4 in November 1967, and it was essentially flawless. That was remarkable because NASA had made the bold and controversial decision to test the Saturn V all up, meaning the very first flight used all 3 live stages at once, rather than testing each stage individually over a series of flights. George Mueller, the head of NASA's Office of Manned Spaceflight, had pushed this approach over the objections of von Braun and many other engineers who preferred the more conservative step-by-step method. Mueller argued that the step-by-step approach would take too long to meet Kennedy's end-of-decade deadline. It was a calculated gamble, and it paid off, but Apollo wasn't without tragedy. In January 1967, 10 months before that first Saturn V test flight, astronauts Gus Grissom, Ed White, and Roger Chaffee were killed during a launch pad test of the Apollo 1 command module. A fire broke out in the pure oxygen atmosphere inside the capsule, and the crew couldn't open the inward opening hatch fast enough to escape. The fire spread with terrifying speed in the high-pressure, pure oxygen environment, and all 3 men died within seconds. The investigation revealed a cascade of design problems, exposed wiring, flammable materials throughout the cabin, a hatch design that was almost impossible to open quickly, and the decision to use pure oxygen at above atmospheric pressure during ground tests. It was a devastating failure, and it nearly ended the Apollo program. NASA essentially stopped everything and spent 18 months redesigning the command module. They replaced flammable materials with fire-resistant ones, redesigned the hatch to open outward quickly, changed the atmosphere for ground tests to a nitrogen-oxygen mix, and overhauled their safety review processes. The redesigned spacecraft was profoundly safer, and some historians argue that the fire, as horrible as it was, ultimately made the moon landings possible by forcing a level of rigor and attention to detail that might not have existed otherwise. That's a painful kind of progress, learning written in human cost. By July of 1969, after several more Apollo missions that tested various components in Earth and lunar orbit, everything was ready. Apollo 11 launched on July 16th, carrying Neil Armstrong, Buzz Aldrin, and Michael Collins atop a Saturn V from Launch Complex 39A at Kennedy Space Center. The first stage burned for 150 seconds, the second stage for about 6 minutes, and the third stage fired twice, once to reach orbit and again for the translunar injection that sent them toward the moon at about 39,000 kilometers per hour. And here's something that doesn't get talked about enough. The journey to the moon took about 3 days. 3 days of coasting through the void between Earth and the moon, with only minor course corrections along the way. Most of the energy was spent in those first 12 minutes of powered flight. After that, it was Newton's first law doing the work. An object in motion stays in motion. The spacecraft was falling, really, following a trajectory shaped by the gravitational pulls of Earth and the Moon, a path calculated so precisely that by the time they arrived, they could slip into lunar orbit with a relatively brief engine burn. The lunar module, that spindly, strange-looking spacecraft that actually landed on the Moon, is a whole story in itself, and it represents a kind of engineering philosophy that's almost the opposite of the Saturn V's brute force approach, where the Saturn V was enormous and powerful. The lunar module was fragile and minimal. It didn't need to be aerodynamic because it would never fly through an atmosphere. It didn't need to be strong enough to withstand high accelerations because its descent engine throttled gently. Its walls were so thin. In some places, the aluminum skin was about the thickness of 2 layers of heavy-duty aluminum foil, that a technician once dropped a screwdriver and it went right through the hull. Every gram mattered because every gram had to be lifted off the Moon's surface for the return to lunar orbit, and that meant every gram needed fuel, which itself had mass, which needed more fuel. The rocket equation again, always the rocket equation, governing every decision. The descent engine on the lunar module was one of the first throttleable rocket engines ever built for spaceflight. Most rocket engines of that era were either on or off. You couldn't vary the thrust, but landing on the Moon required precise control. The astronauts needed to slow down gradually, hover, look for a safe landing spot, and set down gently. The descent propulsion system, built by TRW, could throttle from about 10% to full thrust, giving Armstrong the control he needed when he took over manual piloting during the final minutes of the Apollo 11 landing, guiding the lunar module past a boulder field to a safe touchdown in the Sea of Tranquility with about 25 seconds of fuel remaining. 25 seconds. That's how close it was. And that razor-thin margin tells you something important about the nature of spaceflight engineering. You are always operating near the edge because the rocket equation demands it. You can't carry comfortable reserves of fuel because fuel is heavy, and carrying it means you need more fuel to carry it. So you calculate your margins carefully. You trust your engineering, and you accept a level of risk that would be unthinkable in almost any other field. After Apollo, the story of rocketry takes a different turn. The moon race was won. The political urgency faded, and budgets shrank. But the engineering didn't stop. It evolved in directions that the pioneers might not have predicted. And one of the most ambitious and controversial projects to emerge from the post-Apollo era was something that promised to make spaceflight routine, affordable, and reusable. It was called the Space Transportation System, but everyone knows it by its simpler name, the Space Shuttle. and the engineering choices that went into the shuttle, the compromises that were forced on it by politics and budget constraints, would shape American spaceflight for 3 decades and lead to both remarkable achievements and 2 devastating tragedies that would force the entire nation to reckon with the true cost of reaching space. So let's talk about what the shuttle actually was, because it's one of the most complicated flying machines ever built, and the story of how it ended up looking the way it did is a lesson in what happens when engineering vision collides with political reality. The original idea, back in the late 1960s, was genuinely bold. NASA wanted a fully reusable 2-stage vehicle, a big crewed booster that would fly back and land like an airplane, carrying a smaller orbiter on its back that would continue to orbit. Both pieces would return, both would be refurbished, both would fly again. In theory, this would slash the cost of getting to space, because you wouldn't be throwing away your rocket every single time. Think about how wasteful Apollo was from a hardware perspective. That glorious Saturn V, all 3 stages, the lunar module, the service module, all of it discarded. The only thing that came back was the tiny command module bobbing under parachutes in the Pacific. Billions of dollars of hardware used once. The shuttle was supposed to fix that, but fully reusable meant expensive to develop. The estimates ran into the tens of billions, and this was the early 1970s. With Vietnam winding down, social programs competing for funding, and Congress in no mood to write NASA another Apollo-sized check, so compromises began. The fully reusable booster was dropped. Then the design went through iteration after iteration, each one shaving development cost, but adding operational complexity. What emerged was a hybrid, part reusable, part expendable. And honestly, it was an engineering marvel that never quite delivered on its economic promise. Here's what you ended up with. The orbiter itself, the part that looks like an airplane, that was reusable. It had 3 main engines called the Space Shuttle Main Engines, or SSMEs, built by Rocketdyne. And these were genuinely extraordinary pieces of engineering. Each one produced about 470,000 pounds of thrust at sea level, burning liquid hydrogen and liquid oxygen at a chamber pressure of around 3,000 pounds per square inch, the highest of any rocket engine that had flown at that point. And here's what made them special. They were staged combustion engines. Remember how we talked about the challenges of turbopumps, how you need enormous power just to force propellant into the combustion chamber. In earlier engines like the F1, the turbopump exhaust was dumped overboard, which meant you were wasting some of your propellant. It went through the turbine but never got fully burned in the main chamber. That's called an open cycle, or gas generator cycle. The SSMEs used a closed cycle, where the turbopump exhaust was routed back into the main combustion chamber and burned completely. Nothing wasted. This gave them a specific impulse of about 452 seconds in vacuum, which was remarkable, even better than the J2 hydrogen engines on the Saturn V's upper stages, and they were throttleable from 65% up to 109% of their rated power level. They were designed to be used, inspected, and flown again, mission after mission, but the orbiter couldn't carry enough propellant internally. The mass would have been prohibitive. So the hydrogen and oxygen were stored in that big orange external tank, the most visible part of the shuttle stack. That tank was the one piece that wasn't reused. It was discarded during ascent, tumbling back into the atmosphere to break apart over the ocean. So right there, you've lost full reusability. Every flight needed a new external tank, and those weren't cheap. And then there were the solid rocket boosters, the two white pillars strapped to the sides. This is where one of the most consequential compromises happened. Solid rockets are simpler and cheaper to develop than liquid engines, and the contract to build them went to Thiokol Chemical Corporation in Utah. Each booster produced about 2.6 million pounds of thrust at ignition, and together they provided most of the shuttle's liftoff thrust. They burned for about 2 minutes, then separated and parachuted into the Atlantic to be recovered, refurbished, and reloaded with propellant. So they were reusable too, in a sense. But here's the thing about solid rockets. Once you light them, they burn until the propellant is gone. You cannot shut them down. You cannot throttle them. If something goes wrong in those first 2 minutes, you are riding a lit firework with no off switch. That fundamental characteristic would prove catastrophic. Each solid rocket booster was assembled from segments, cylindrical sections, manufactured in Utah and shipped by rail to Kennedy Space Center in Florida, where they were stacked and joined together. The joints between those segments were sealed with rubber O-rings, and the design of those joints, the way they flexed under pressure and temperature, became the most scrutinized engineering detail in the history of spaceflight. Because on January 28, 1986, the Space Shuttle Challenger broke apart 73 seconds after launch, killing all 7 crew members, including Krista McAuliffe, a school teacher from New Hampshire who was to be the first ordinary citizen in space. The cause was an O-ring failure in the right solid rocket booster. The morning of the launch was unusually cold for Florida. Temperatures near the pad had dropped to around 36 degrees Fahrenheit overnight, well below the design qualification range for the O-rings. Engineers at Thiokol had actually recommended against launching. They argued the night before in a teleconference with NASA managers that the cold would stiffen the O-rings and prevent them from sealing properly when the joint flexed during ignition. The data was ambiguous in some ways. There hadn't been enough cold weather launches to build a complete statistical picture, but the concern was real and it was specific. NASA managers pushed back. There was schedule pressure. There was political pressure. There was a culture that had gradually normalized risk after 24 successful shuttle missions. The engineers were overruled. The launch proceeded, and 73 seconds in, hot combustion gases burned through the failed O-ring joint, reached the external tank, and the vehicle was torn apart by aerodynamic forces. The Rogers Commission, chaired by former Secretary of State William Rogers and including the physicist Richard Feynman, investigated the disaster. Feynman's contribution became legendary. During a televised hearing, he took a small piece of O-ring material, clamped it in a C-clamp, dunked it in a glass of ice water, and showed that when cold, the rubber lost its resilience. It didn't spring back. Simple, devastating, undeniable. But Feynman's deeper critique went beyond the O-ring. He wrote an appendix to the Commission's report that indicted NASA's entire approach to risk assessment, pointing out that NASA management had estimated the probability of a shuttle failure at 1 in 100,000, while the engineers working on the hardware thought it was closer to 1 in 100. That's a 1,000-fold disconnect between the people making decisions and the people who understood the machinery. Feynman's closing line in that appendix has become one of the most quoted sentences in engineering ethics. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. The shuttle flew again in 1988 after extensive redesign of the solid rocket booster joints. It went on to do extraordinary things. It deployed the Hubble Space Telescope, carried components for the International Space Station, hosted Spacelab science missions, and served as a platform for satellite repair and deployment. The orbiter was genuinely versatile, with a cargo bay 60 feet long and 15 feet in diameter, capable of carrying about 50,000 pounds to low Earth orbit, and the astronauts who flew it will tell you it was an incredible machine to operate, with its delta wing glide profile and unpowered landing approach at over 200 miles per hour, but the economics never worked out. The original promise was that the shuttle would fly frequently. Some early projections imagined 50 or 60 missions per year, and that high flight rate would amortize the costs, bringing the price per pound to orbit way down. In reality, the shuttle averaged about 5 flights per year, and each mission cost somewhere around $450 million to $1.5 billion, depending on how you counted the overhead. That's far more expensive per pound than expendable rockets. The reusability that was supposed to save money actually added cost, because refurbishing the orbiters and boosters between flights turned out to be enormously labor-intensive. The thermal protection system alone, those silica tiles covering the orbiter's belly, each one individually shaped and bonded, required meticulous inspection and repair after every mission. And then, on February 1st, 2003, the Space Shuttle Columbia broke apart during re-entry, killing all 7 crew members. The cause this time was a piece of foam insulation that had broken off the external tank during launch, 81 seconds after liftoff, and struck the leading edge of the orbiter's left wing. The foam punched a hole in the reinforced carbon-carbon panels that protected the wing during the searing heat of re-entry. When Columbia came home 16 days later, superheated plasma entered through that breach and destroyed the wing's internal structure. The orbiter lost control and disintegrated over Texas and Louisiana. The Columbia Accident Investigation Board found echoes of the same organizational failures that had led to Challenger. Foam shedding from the external tank had been observed on previous missions. It had been classified as an acceptable risk, a maintenance issue, rather than a safety of flight concern. Engineers had raised alarms. Management had normalized the deviation. The board's report drew a direct line between the two disasters and concluded that the shuttle's design, with the orbiter mounted beside the external tank and boosters rather than on top, where debris couldn't strike it, created an inherent vulnerability that could never be fully eliminated. The shuttle program ended in 2011 after 135 missions. 2 losses in 135 flights gives you a failure rate of about 1 in 67, which is remarkably close to what those working engineers had estimated back before Challenger. The shuttle was a magnificent and deeply flawed machine, and its legacy is complicated. It proved that you could build a reusable spacecraft. It showed that the engineering of reuse was far harder and far more expensive than anyone had imagined, and it demonstrated, painfully, that organizational culture and decision-making processes are as much a part of engineering safety as the hardware itself. But even as the shuttle was flying, the rest of the world's rocket engineers were taking different approaches. The Europeans developed Ariane. The Russians kept flying their Soyuz and Proton vehicles, descendants of Korolev's original designs, and a new generation of thinkers started asking a question that would reshape the entire industry. What if you could make a rocket reusable, not by building something as complex as the shuttle, but by doing something that sounded almost impossible? Landing a rocket booster vertically, on its tail, the way rockets land in old science fiction movies? The idea had been around for decades. The DCX program in the early 1990s, funded by the Pentagon, had demonstrated a small vertical takeoff, vertical landing prototype called the Delta Clipper. It flew, it landed, it flew again, but it was a demonstrator, not an orbital vehicle, and the program was eventually canceled. The concept seemed promising but impractical at orbital scale. And then, in the early 2000s, a software entrepreneur who had made his fortune from PayPal decided that the cost of access to space was the fundamental bottleneck preventing humanity from becoming a multiplanetary species, and he founded a company in a warehouse in El Segundo, California, with the audacious goal of reducing launch costs by a factor of 10. His name was Elon Musk, and the company was SpaceX, And whatever you think of Musk personally, what his engineering team accomplished over the next 2 decades is one of the most remarkable engineering stories of the 21st century. The thing you have to understand about SpaceX in the very beginning is that almost nobody thought they would succeed, and, honestly, the odds were terrible. Starting a rocket company from scratch is not like starting a software company. You can't iterate in a garage and ship updates overnight. Rockets are unforgiving. They operate at the edge of what materials can withstand, what physics allows, and what human ingenuity can manage. The history we've walked through tonight, from Goddard's little rocket in the cabbage field to the Saturn V to the shuttle, that history is littered with failures, explosions, programs canceled, companies bankrupted. And here was a guy with no aerospace background saying he was going to build orbital rockets cheaper than anyone had ever done it. But Musk did something clever at the outset. He hired people who actually knew what they were doing. Tom Mueller, who became SpaceX's founding propulsion engineer, had been building rocket engines as a hobby, literally in his garage, and had worked at TRW on serious propulsion systems. Mueller designed the Merlin engine, which became the heart of everything SpaceX built. And the Merlin is a really interesting engine to talk about for a moment, because it tells you a lot about SpaceX's engineering philosophy. Remember how we talked about the Space Shuttle's main engines, the SSMEs, and how they used staged combustion to achieve incredibly high efficiency, around 452 seconds of specific impulse. Those engines were engineering masterpieces, but they were also extraordinarily complex and expensive. Each one cost tens of millions of dollars. SpaceX went a different direction. The Merlin uses a simpler cycle called gas generator, where a small amount of propellant is burned separately to drive the turbopumps, and that exhaust is dumped overboard rather than fed back into the main combustion chamber. It's less efficient. The Merlin gets around 282 seconds at sea level, about 311 in vacuum, but it's simpler, cheaper to manufacture, and easier to make reliable. And here's the key insight. If your engine is cheap enough, you can afford to use more of them. You can trade some efficiency for massive reductions in cost and complexity. That trade-off, choosing good enough over perfect, runs through everything SpaceX did. Their first rocket was the Falcon 1, a small 2-stage vehicle designed to put about 670 kilograms into low Earth orbit. It used a single Merlin engine on the first stage and a smaller engine called Kestrel on the upper stage. And the Falcon 1's flight history is one of those stories that, honestly, reads like a movie script. The first launch attempt was in March 2006 from Kwajalein Atoll in the Marshall Islands, this tiny island in the middle of the Pacific that SpaceX leased launch facilities on because it was cheap and far from populated areas. The rocket lifted off, and about 25 seconds into flight, a fuel leak caused an engine fire and it crashed back onto the reef. They fished the wreckage out of the ocean, figured out what went wrong, and built another one. The second attempt was in March 2007. This time, the first stage worked fine, but the second stage developed a roll oscillation. It started spinning, and the vehicle broke apart about 5 minutes into flight. They analyzed, they fixed, they built another one. The third attempt was in August 2008, and this one was heartbreaking. The first stage performed perfectly. Stage separation happened, but the Merlin engine had been upgraded between flights, and the new version had slightly different shutdown characteristics. The residual thrust from the first stage after shutdown meant that when the stages separated, the first stage actually bumped into the second stage a few seconds later, 2 stages colliding in space. The payload, which included the ashes of astronaut Gordon Cooper and actor James Doohan, Scotty from Star Trek, was lost. Now, here's where the human drama matters. SpaceX was running out of money. They had funding for maybe one more attempt. Musk himself was nearly broke. He'd poured his personal fortune into both SpaceX and Tesla, and both companies were on the edge of bankruptcy in 2008. If the fourth Falcon 1 didn't work, that was probably it. The whole venture folds, and SpaceX becomes a footnote in aerospace history, another ambitious startup that couldn't quite make it work. The fourth launch was September 28, 2008, and it worked. The Merlin engine burned clean. The stages separated perfectly. They'd fixed the timing to account for residual thrust. The Kestrel engine lit and pushed the second stage into orbit. Falcon 1 became the first privately developed liquid-fueled rocket to reach orbit. The footage from inside SpaceX headquarters that day, the engineers screaming and crying, is genuinely moving. They'd been working insane hours for 6 years. They'd watched 3 rockets fail, and they'd just pulled it off with essentially their last shot. But the Falcon 1 was always a stepping stone. Even before that fourth flight, SpaceX was already designing the Falcon 9, which is the vehicle that really changed the industry. The concept was straightforward in principle. Take 9 Merlin engines, cluster them on a first stage, and build a rocket that could put serious payloads, around 13,000 kilograms initially, later upgraded to over 22,000 into low Earth orbit. The name literally tells you the design: Falcon 9 engines. And that clustering approach is worth thinking about because it connects back to a problem we talked about much earlier tonight. Remember the F1 engines on the Saturn V and how achieving stable combustion in a single enormous engine was one of the hardest engineering problems of Apollo. SpaceX sidestepped that entirely. Instead of building one giant engine, they used many smaller ones. Each Merlin produces about 845 kilonewtons of thrust at sea level in its latest version. 9 of them together give you roughly 7,600 kilonewtons, not as much as the Saturn V's first stage, but in the same neighborhood as many heavy lift vehicles. And the clustering gives you something else: redundancy. If one engine fails during flight, the remaining 8 can compensate. The flight computer adjusts the burn time and throttle of the remaining engines to still reach the target orbit. SpaceX actually demonstrated this in flight. A Falcon 9 lost an engine during ascent in 2012 and still delivered its payload successfully. You can't do that with a single engine stage. The first Falcon 9 flew in June 2010, and it worked on the first try. Over the next several years, SpaceX systematically improved the vehicle while also developing the Dragon spacecraft, which became the first commercial vehicle to berth with the International Space Station in 2012. But the thing that really captured the world's imagination, the thing that made people who'd never thought about rockets suddenly pay attention, was the landing. Let's talk about what it actually takes to land a rocket booster vertically, because it's one of those things that looks almost magical when you watch it. But the engineering underneath is beautifully logical. When a Falcon 9 first stage separates from the second stage, it's moving at several thousand kilometers per hour, high in the atmosphere or just above it. To come back and land, it needs to do 3 things: flip around so the engines are pointing forward, slow down enough to survive re-entry into the thicker parts of the atmosphere, and then perform a precision landing burn to touch down gently at a specific spot. The flip is handled by cold gas thrusters and grid fins, those waffle-shaped panels near the top of the booster that you might have seen in footage. Grid fins are an old technology, actually used on some Russian missiles, and they work well at both subsonic and supersonic speeds, giving the booster aerodynamic steering on the way down. The re-entry challenge is managed by what SpaceX calls the boost back burn and the entry burn, 2 separate engine firings that redirect the booster toward the landing site and slow it down enough that aerodynamic heating doesn't destroy it. And then the final landing burn is the really tricky part. Here's the thing about the Merlin engine. Even at its lowest throttle setting, a single engine produces more thrust than the nearly empty booster weighs. That means you can't hover. Think about what that implies. If you light the engine and it's producing more force than gravity is pulling you down with, you're going up, not hovering in place. So the landing burn has to be timed perfectly. You light the engine at exactly the right altitude and speed, so that by the time you've decelerated to 0 velocity, you're also at 0 altitude. You get one shot. There's no hovering to make corrections. The engineers call it a hover slam, or more formally, a suicide burn, and the math has to be precise. The onboard computer is running continuous calculations, adjusting the engine gimbal and throttle in real time, guided by GPS, inertial sensors, and radar altimeters. SpaceX tried to land boosters several times and failed, spectacularly in some cases. There's a compilation video Musk released titled How not to land an orbital rocket booster that shows booster after booster crashing into drone ships, tipping over, exploding on the pad. They were learning in public, which is unusual for aerospace. But in December 2015, a Falcon 9 first stage landed successfully at Cape Canaveral's Landing Zone 1. And in April 2016, one landed on a drone ship at sea, and then it just kept working. As of the mid-2020s, SpaceX has landed and reflown Falcon 9 boosters well over 300 times. Individual boosters have flown more than 20 missions each. The turnaround time between flights has dropped to weeks, sometimes days, and this is where the economics shift. Remember the tyranny of the mass ratio, how most of a rocket's weight is propellant? Well, the propellant in a Falcon 9, kerosene and liquid oxygen, costs roughly $200,000 to $300,000 per flight. The rocket itself costs tens of millions to build. If you throw it away every time, your launch costs are dominated by hardware. If you reuse it, suddenly the cost per flight drops dramatically. SpaceX brought the cost of putting a kilogram into low Earth orbit down from something like $20,000 or $30,000 on older vehicles to under $3,000. That's not quite the factor of 10 reduction Musk originally promised, but it's close, and it reshaped the entire launch industry. Competitors, United Launch Alliance, Arianespace, Roscosmos, suddenly found themselves trying to match prices they'd never imagined. And SpaceX didn't stop there. The Falcon Heavy, first flown in February 2018, straps 3 Falcon 9 first stages together to create a heavy lift vehicle that can put over 60,000 kilograms into low Earth orbit, making it the most powerful operational rocket at the time. And then there's Starship, which is something else entirely. Starship is SpaceX's fully reusable super heavy lift vehicle, and it's designed to be the most powerful rocket ever built, more powerful than the Saturn V. The first stage, called Super Heavy, uses 33 Raptor engines, and the Raptor is a fundamentally different engine from the Merlin. Remember how I said SpaceX chose the simpler gas generator cycle for the Merlin? With Raptor, they went the other direction, full-flow staged combustion, where both the fuel-rich and oxidizer-rich pre-burners drive separate turbopumps, and all the exhaust from both pre-burners goes into the main combustion chamber. It's the most complex and efficient engine cycle there is, and before Raptor, no engine using full-flow staged combustion had ever flown. The Soviets developed one called the RD-270 in the 1960s, but never flew it. Raptor runs on liquid methane and liquid oxygen, achieves a specific impulse of about 350 seconds at sea level, and operates at chamber pressures over 300 bars, extraordinarily high. The engineering challenges of that are immense, but the efficiency gains matter when your goal is full reusability and eventually refueling in orbit for deep space missions. Starship's upper stage, also called Starship, which is a little confusing, is itself designed to land vertically and be reused. The whole system, both stages, comes back if it works as intended, and the early test flights in 2023 and 2024 showed both spectacular progress and spectacular failures, booster stages being caught by the launch tower's mechanical arms, upper stages breaking apart during re-entry. If it works, the cost per kilogram to orbit could drop by another order of magnitude. We might be talking about hundreds of dollars per kilogram. At that price, everything changes. Space stations become cheap. Lunar bases become plausible. Mars missions move from science fiction to engineering problems with price tags, and SpaceX isn't alone anymore. Blue Origin, founded by Jeff Bezos, has developed the New Shepard suborbital vehicle and the much larger New Glenn orbital rocket with a reusable first stage. Rocket Lab, a smaller company founded by Peter Beck in New Zealand, has been flying the Electron rocket since 2018 and is developing a medium-lift reusable vehicle called Neutron. China's space program has grown enormously, with the Long March 5th heavy-lift vehicle and multiple commercial startups developing reusable rockets. The entire industry has shifted. Reusability isn't a novelty anymore. It's the expectation. So where does all of this leave us? You've been lying here, maybe drifting in and out, and we've traveled a long way together tonight. We started with the simplest possible idea, Newton's third law, the principle that every action has an equal and opposite reaction, the thing that makes a balloon fly across the room when you let go of it. We went to ancient China, where gunpowder packed into bamboo tubes became the first rockets. We sat with Tsiolkovsky in his log cabin in Kaluga, working out the mathematics of space travel decades before anyone had the technology to attempt it. We stood in a snowy field in Auburn, Massachusetts, watching Goddard's little rocket rise for 2.5 seconds. We followed von Braun through the darkness of Peenemünde and the horrors of Mittelwerk to the triumphant thunder of the Saturn V. We remembered Korolev, the man who launched the space age from behind the anonymity the Soviet system imposed on him, who never lived to see humans walk on the moon. We walked through the physics, thrust and specific impulse and mass ratios and staging, the brutal arithmetic that makes spaceflight so hard. We watched Apollo succeed against extraordinary odds, and we watched the shuttle program teach painful lessons about the gap between ambition and reality, about how organizations fail even when their engineers are brilliant. And now here we are, in a moment where rockets land on their tails like something out of a Tintin comic, where private companies are doing what only superpowers could do a generation ago, where the cost of reaching orbit is falling fast enough that the next chapter of this story, whatever it turns out to be, might be written not by governments, but by thousands of engineers in dozens of companies around the world, solving problems we haven't even identified yet. That's the thing about engineering. It's never finished. Every solution reveals new problems. Every breakthrough opens new questions. The rocket equation doesn't care about your ambitions. It's just math, patient and absolute. But human ingenuity keeps finding ways to work within those constraints, to shave off a few more seconds of specific impulse, to make the structures a little lighter, to recover and reuse what used to be thrown away. The story of rockets is really the story of people refusing to accept that something is impossible. Going back to the workshop, running the numbers one more time, building another prototype, watching it explode, and building another one. So as you settle in and let sleep take you, carry that thought with you, that quiet stubbornness, that willingness to try again, the same physics that holds you gently in your bed right now, the gravity pulling your body into the mattress, is the force that every rocket ever built has had to overcome. And every time one of them clears the tower and climbs into the sky, trailing fire, it's because someone, somewhere, did the math, bent the metal, solved the problem, and lit the candle. Sleep well. The rockets will still be flying in the morning.